Hey, welcome back. Today I want to talk about one more interesting machine learning algorithm. We have also looked at XGBoost in the past, but I do want to go more elaborate, go over important steps in the model building process, from data engineering steps such as pre-processing, changing the categorical variables into more interpretable forms using label encoders, understanding the correlation between x and y variable, and a lot of nitty gritties and nuances. So from identifying the variables that could make a difference to the predictor variable to go into nitty gritties of how we can change and improve the accuracy. We will also discuss about two other alternative methods apart from XGBoost methodology to be able to get a sense of which is more accurate. And we will talk through some of the trade-offs that are in place, why use a certain alternative algorithm versus XGBoost, and how does it make an impact to the business from a computational standpoint, from time optimization, time and space optimization, and also accuracy, which is also a very important step to roll out a machine learning algorithm into. Starting with the very first step, which is import all the relevant libraries. I'm going to write a couple of them and bring in the rest in the best interest of time. Import pandas, SPD, one of the most important to be able to compute or do any pre-processing. NumPy as NP, you already know that. And going to bring Matplotlib. We do want to see some correlation studies. .pyplot, SPLT. And I want to bring in the rest of the libraries too in the best interest of time. We do want to bring in XGBoost, CatBoost, and LightBoost. These are three different alternative methods we want to try today. So I have all that. So I'm going to quickly label these. This is the model evaluation criteria. And we have, this is the XGBoost model. It's called the extreme gradient boost model. And this is the light gradient boost, which is computationally more efficient in case of large big data. If you're not really worried about high accuracy, you don't have to do those high number of iterations and keep it computationally efficient. So this is category boost model. It is an alternative when you have a lot of categorical variables in your independent list of variables. So yeah, we have all the libraries we need. Let's get started. Now we're going to define the data frame, and I'm going to define the data frame and read it from the CSV file. Copy the file path that we have here. So it's going to help us read the data. Okay, now that we have read the data, we want to print df the top 10 rows. Let's just print the top 10 rows. To get a better sense of what the data looks like. So let's do that. Okay, so we have all the data in here. So there are about little over 10 columns here. Patient ID is the primary indicator. We have the age, we have gender, country, which is the region, last 10 years worth of information. So we have year as one of the columns. Genetic risk. This is a scale which is helping understand there is a genetic condition or hereditary factors that can be influencing the cancer. The onset of cancer. So we have air pollution. This is one of the factors, alcohol consumption, smoking, obesity, the type of cancer, and the stage of cancer as well. So we will slowly evaluate what can be the best predictor variable we want to evaluate depending on the factors that we have here. So let's get right to it. I do want to quickly look at the high-level summary stats. So this is to get summary statistics like mean, minimum value, max, the quartiles, like 25%, 50%, 75% quartiles. And we also have standard deviation, which is going to help us understand the distribution much better. So let's try and run that. So we have a total of 5,000 rows. You can clearly see the quartiles are very well distributed, which talks about how symmetrical the data is. That is good news. Since the data is symmetrical, the difference between the 25% and 50% and 75% quartiles is uniform. That says the graph, the distribution is symmetric. And in case of null values, we can simply replace them with mean in this context because the data is symmetrical. So let's get right to it. Some of the key hypotheses I want to talk about today is I do want to identify the target severity score. So that's how I'm going to define my y variable, and some of the key factors I think will influence this particular target variable, which is the severity score of this cancer. What combination of factors give us the best accuracy of cancer prediction? That is a step beyond the actual prediction, which is trying to help understand the correlation between the y variable and the independent variables. So let's quickly define these variables. I'm going to define them as df. To bring in all the data, there is a much easier way to get all the different rows than simply copy them. It is the column list. So let's get the column list. And then we can just print the list of columns we are getting in the previous row. So this will help us get to all the columns that we need instead of, okay, I think that the data frame has some error in the, okay, so we have the list of all the columns in this data set. So we'll bring that over here, and then we can simply define what is the relevant factor for x variables, y variable, and also break them down into numerical and categorical variables. So I'm going to copy all of them under numerical, and then I'm going to methodically move them to categorical variables in this context. So I'm going to bring the categorical variables separate. We have different methodologies to evaluate the categorical variables. So patient ID is not quite needed. It is the primary indicator. Country, region is definitely a categorical variable. So I'm going to move that here. We don't need it here. Year is gender. Gender is a categorical variable as well. So I'm going to move that here. Here is a continuous variable, so I'm going to get rid of that. Genetic risk, air pollution, alcohol consumption, these are all numerical or continuous variables, so I'm going to move them from here. The cancer type and cancer stage are definitely categorical variables. I don't believe we're going to be using that in this particular exercise. They're good information, so treatment and survival years are not going to be of any interest at this point as well. So the predictor variable, as like we talked about, it's going to be the y variable or the predictor variable of what's the accuracy with which we can predict cancer. This is my definition of predictor variable here. So let me comment this out to prevent any future errors. We have that taken care of. So again, one more quick look at this information. So we have all the continuous variables here. We should move the cancer type and cancer risk from out of here. The y variable is also not part of the numerical variables. So we have everything we need. We have age, year, genetic risk, air pollution, alcohol use, smoking, obesity level, treatment. We don't really need that. Survival years, we don't really need that. So I'm going to get rid of them as well. Okay, we have defined all the variables that we need. Now we can go forward. I do, however, want to change the age and year into categorical variables, which is easier for the model to understand. So how I'm going to do that? Let's define a simple we're done with step number 4. Now we're jumping on to step number 5, how to identify or define age group. So we're going to define age series. And how we are going to define age series, we're going to first initiate a null array or empty array for age in age series. We want to define the different range of age, and then categorize into them into groups between 20 to 30, 30 to 40, and 50 plus. Okay, so we're going to define the range. In this context, we're going to 30. If the age is in this group, then we want to append to the age group 20 to 30. Okay, that's good enough. So now we are going to redo the entire step to define the new range, which is, let's say, from 30 to 40. We do want to make sure these are the ranges are mutually exclusive. So I'm going to change the 30 to 31. So the ranges of age groups are mutually exclusive. So once we define this function and make it mutually exclusive, we can jump on to the next step. So here we are saying it is 40 to 50. Change the same thing. And the last category of the age group we want to think about is 50 plus. the age is greater than 50, then we want to append 50 plus. Okay, that's pretty good. And now instead of else if, we're going to change it to elif. It's a way we want to define the function. Now we have else. We do want to define the age group. In case of any erroneous values, we want to define it as a new group by itself. So we're going to call that as other, and we have everything we need so far. Simply get the age group. Now that we have defined the age group as a new column, we need to bring that into the data set. Age group. And after defining this as, we want to bring the original function, which is category age, and the way we want to define it as the series of numbers that we want to input for this age group categorical variable is from the column age. So that should take care of it. Let's try and run this snippet of code. Okay, so we can quickly evaluate how this is working. We can take a look at the first 10 rows to see if the age group is part of the new data set or not. Yep, we have the age group, and it looks like it is working as expected. So moving on to the next one. I do love to change the year as well, but I do not think it's one of the major variables for categorical, the set of categorical variables. So since we created a new column in the categorical list of variables, I'm going to redefine that and say bring the age group into this. We can move that from the continuous variables and add that into the categorical variables. So now we're going to rerun this, all the variables that we have newly created. Okay, that's perfect. Now we want to replace the null values. So we have two simple ways to tackle this. One is to replace the null values for numerical variables, and the other one to replace the categorical variables using a simple string called unknown. So let's get to that. So we are going to define a function in this context as well. The data set, we have a function called dtypes, and we are going to include to check if it is a number. This is an automated way. We don't have to select all the columns. We don't have to specifically select every single column that has numerical variables. We just need to use this function, dtypes include number. That's going to help us quickly get to the columns that we need, which are in the number data type, and just use fill NA as a fill to be able to change the null values or replace the null values with the mean value. So we bring in the mean. So let's take a quick look at this definition. For columns in DF, select dtypes include number. For all such columns, we want to change or replace those columns, the null values with the value of mean. Since it's a symmetrical data set, we already looked at the different quartiles. We are okay to change or replace the null values with mean, and that's not going to change the characteristics of the distribution. Okay, so now that's complete. We have very similar scenario for the categorical variables. We're going to change that into string. In case of string, what we're going to do is we don't have to go over the whole process, but just change it with a simple string called unknown. So let's rerun that piece. So we've already done this part. We have isolated the numerical and categorical variables here well ahead of time. So that's taken care of already. Now we will use label encoder to convert or transform the categorical variables in a way that the model can understand better. So we will first initiate the label encoders, and only for the categorical variables, we need to do the transformation. X categorical feature label encoder, which we have imported in the past above. So we'll bring that in and simply categorical. Okay, so that should take care of label encoding. quick lookup to see we are only taking care of the X categorical variables which we have defined over here. And then we're going to transform it using the label encoder. So that's going to take care of that. Let me run that step real quick. Okay, that's complete. Now combine both the data sets. So I'm going to call this X as the combined data set. pd.concat is a quick function to combine data sets. X numerical, comma, X categorical. Some mandatory steps that we need to follow to be able to run that, and we have that complete. So once we are done with running or combining the data set, now we are going to do the model building process. In this, the most important piece is to dissect the data into train and test samples. So we're going to do that step real quick. X test, X train, Y train. Order doesn't matter, I guess, but we're going to keep it symmetrical and easy to understand. X test, Y train, Y test is equal to train, test, split, X variable, Y variable, test size. I'm going to define that as 20%, and random state. This is used to, when we do multiple iterations, we don't want to land with completely different results. That's the way to keep check on how many. Let's continue to build this model. We are on step number 12, where we are going to call the type of model we want to create. XGB, let's call that XGB model, and define the XGB model from the library we have imported earlier. XGB regressor is the type of the model we want to bring in, and we're going to define some of the hyperparameters. The objective here is mean squared error. Yep, that should take care of it. So we have, this is the train method. Some of these comments are going to be helpful. So now we have the n estimators, which is, we can start with 100. It is going to help. It's basically the number of iterations. And now we want to identify the max depth. Similar to decision trees, it is a simple number. We understand that. So we want to also get random state. The same purpose, to be able to make sure we're not getting very different values each time we rerun the model. So now we have all that set. Now we're going to run the model XGB model dot fit. We're going to get X train, Y train. We're going to train it using the training sample, which is the 80% split we have done earlier. And then we're going to get the model accuracy testing done against the test sample split, which we have done also. So Y predict is equal to XGB model dot predict on the test sample. So that's good to go. Now we do want some of the model evaluation criteria. So we do add that. Evaluate the model. Let's start with model evaluation criteria. Root mean squared error is the first one. We have mean absolute error as the second one, and then we have R squared as the third one. In the best interest of time, I'm going to run through one of the examples, and then we can talk through the rest. So we have mean squared error. We want to determine between the Y test and Y predict. And bring in root mean error. Let's see. Okay, very similarly, we are going to bring in the mean absolute error and the R squared as well. So we got that. For visualization, this is an important step. I think I do want to take a second here to talk through what we're trying to achieve here. We're trying to understand the correlation between the X variables, independent X variables, and the predictor variable. So that's what we're trying to plot here. So we are going to bring in the X and Y variables for starters. We're specifically interested in X variables, numerical variables. We're not going to worry about categorical variables in this context. So we have defined the X numerical variables and Y variables. So we are going to do a simple correlations function. and that's going to be very simple. We're going to define a relationship between the numerical variables and use correlation with y, and then sort values. Some of the syntax to help with the correlation function here. And then we want to create a simple horizontal bar chart to understand the correlation between x and y variables. So PLT, Matplotlib, we're going to use this library and bring up some of the visualization aspect to it. Now we are going to bring in the correlations function. We have used above and plot a bar chart. And then we want to also mention which color we want to plot the bar chart. Okay, so that's done. We have 3 simple steps. We have X label, we have Y label, title. We want to define the grid, plt dot. For X label, we just want the correlation weights. For Y label, we need the X variables to be displayed, and title is correlation analysis with independent variables. Okay, and let's define the grid. Line style. So that should take care of it. We have defined the correlation. Yeah, we have come to almost the end of this modeling technique. We want to quickly run this correlation analysis and then see what the output is, so we can get a better understanding of how the X variables are correlated with Y. So this is a beautiful chart where we can clearly distinguish between smoking as an indicator to predict cancer versus genetic risk versus air pollution, alcohol use, and obesity. It also helps us or guides us in a much clearer way how to identify some of the X variables. So a combination of these factors could help understand where we can get the maximum accuracy. So having said that, that is a correlation analysis is outside of the modeling, but it is going to be very, very helpful to understand and determine how each one of these X variables are influencing the predictive variable. In this context, it is the prediction of cancer. I do want to touch on the alternative methods that we can leverage while building an XGBoost methodology, which is going to be very helpful with respect to computation. And category boost model is also computationally very efficient. And at the same time, when there are more categorical variables you want to include in your model, that is a great alternative to have. So that's all for today. I do want to quickly run the model evaluation metrics and understand what is the accuracy we are achieving. And of course, we can slice and dice and improve that accuracy as needed. So we do see 77% R squared value, mean absolute error is 0.48, and root mean squared error is 0.32. That is, those are some helpful numbers with the modeling criteria. And further, we can fine tune the parameters within the model, such as the maximum depth. You can also improve the number of iterations. If you are reducing the number of iterations, which is n estimators right here, and the accuracy is not decreasing, you are better off reducing the number of iterations. So these are some hyperparameter tuning techniques that you can adapt to help to increase the cost efficiency and at the same time keep the accuracy at the maximum value we can obtain. So that's all for today. We'll catch up soon, and I hope you enjoyed today's modeling technique